there we go for the logistic regression, and both of them have immense applications in real life situations and also in the respective research, not only from in the statistic group, but all over the other areas of basic science. And they extensively use, and we will give particularly emphasis how to interpret all those results when you have applied some kind of data analysis technique. Okay, so again, we'll go back to the research question. So I particularly want to emphasize that whenever you do it, you just should not do in mechanical way. You have to understand that the linear regression or any other statistical methods, that those are basically tool. So that is just helping to it. Those methods are not important as much as the research question. So research question is the main thing, whether you can get something. Some people are maybe sometimes fond of that. Those are very sophisticated methods. So it doesn't matter what kind of methods you are using. Those are some basic tools, and you are applying those tools to get some answer. So the answer is much more important than the model itself. So at the end of the day, whether are you able to interpret the results, whether are you able to improve the situation that is existing in that particular basic science area, that is much more important. So we'll start with that basic research questions that we already started. So what is the impact of attending classes, regular study hours, and sports time on students' final marks? So earlier we have seen the impact of attending classes on the student marks. Now in the same problem, we want to also understand the importance of the regular study hours and the sports time on the student final marks. So now the problem become in a sense of multivariate. Now the source of explanation is not only the attending classes. So a student in realistic situation will attend classes, will study several hours by themselves, and also they will participate in different sports activity. So all those things, how they contribute to the student final marks. So there are other factors also, but at this time point we are not considering anything. But I do not have that this one, so I will not be able to show with respect to data. This is just for your motivational purpose there. Okay, so simple linear regression that you have already learned yesterday is considered only one independent variable. By independent variable, I mean the X variable. Okay, and however, here we have three independent variables: attending classes, regular study hours, and sports time. You can consider them X1, X2, and X3. Okay, so another important thing is that somebody yesterday was talking about the multi-collinearity. This is the collinearity. Notice that the correlation between the attending classes and the regular study hours. So it is expected those students who attend classes regularly are also the students expected to study regularly. This is called the multi-strong correlation. And what is the intuitive explanation of this one? When my X1, X2, they are correlated, I will not know exactly in a certain way that whether the impact of the attending classes on the final marks or the regular study hours, because they are interrelated. So mathematically saying, I will have some problem in estimating all those parameters. The parameter estimation will not be as accurate as possible when these things are correlated, and we'll explain a little bit, not in detail here. Okay, so we can use the multiple linear regression. Multiple in the sense we have by linear. Right now, I am talking about the linear in parameters, not in the variables. Okay, so when we have more than one independent variable in the regression setup, we go for the multiple linear regression. Okay, so this is pretty much simple for you. Now we have P equal to more than one predictors, and our multiple linear regression line can be written as yi to be beta naught, beta 1 xi1 up to the beta p. So we have p plus 1 parameters. Okay, so we have p many variables and one intercept, that is we have p plus one parameters here. And as before, the basic assumptions of the linear regression still valid. Epsilons are need to be IID. IID means that independent and identically distributed with expected value of epsilon to be 0 and variance of epsilon to be sigma square, that is the constant variance. I'm not talking about the normality, but if you are going for the inference, of course, you need the assumptions that epsilon I follows a normal 0 sigma square for all I. Okay. So scalar notation becomes cumbersome, so we will use the matrix notation. I will not go into much detail as yesterday. I'll just state the results, how the things are going on because of the lack of time. So here that notice that we have a number of observations, or you can say a number of patients or a number of participants in a study where we are intended to fit multiple linear regression. Okay, so that means that for each of these observations, I will have y1, y2, yn. So this is my, so for talking about the marks obtained by students in a class, so y1 will be the number obtained by the first student, and yn will be the, and this x matrix, so each row of this matrix corresponds to the student. So marks obtained by the first student is y1, and x2 1 you can say that number of classes attended, and if you have x 1 2, that means that will be the number of average study hours of that first student. And say for example here p equal to 3, that means x3 will be the what was that, the average sports activity. So each row of the X matrix corresponding to a particular individual and their corresponding observations of the independent or explanatory variables. Similarly, this row corresponding to the nth student whose obtained marks is yn, and this is the, if I am talking about ny1, that means that number of classes attended, and if we have x here x n2, that will be the average study hours, and if we have p equal to 3, that means n3, that will be the whatever the average sports activity, that kind of things. So this is the x pretty much, and this 1 represent all those cases. This is the intercept term. So for all them in corresponding to that x values will be 1, so that matrix remain valid. And here the parameters, earlier we have only 2 parameters, beta naught and beta 1 there, and here we have p plus 1 parameter. First parameter is the intercept, and all the other parameters corresponding to the each of the x variable or independent variable there. And similarly, the error term corresponding to each of the participant, I will have 1 corresponding error term starting from epsilon 1 to epsilon n. And this entire thing can be written in a very short form, that y, this is the n cross 1 vector. Okay, I have n rows and 1 column, that is n cross 1. This is rows and this is column. Similarly, this matrix have n cross p plus 1 column. So you have up to this p, and this is 1, that is p plus 1 column. And here we have 0 up to p, that means p plus 1 cross 1, p plus 1 rows and 1 column. Similarly, here we have n cross 1. Now, when I am multiplying this, you need to have the, I'm multiplying x with beta. That means the columns of x has to be equal to the exact number of rows, that is p plus 1 in both cases, so that matrix multiplication remain valid there. So this is the compact form of the regression model in case of multiple linear regression. Okay. So there are certain names. X is called the design matrix, and you can denote in general as the regression model y equal to x beta plus epsilon, where y generally the outcome, x is the design matrix, or all the information that you may think of with respect to the independent variables is concentrated on there. and beta is a parameter vector. It is not a single quantity. It's a vector, and epsilon is also vector, or I will call the error vector, or sometimes it is called the random vector rather than a random variable. Assumptions is there, like expected value of epsilon needs to be 0, and variance of epsilon needs to be a constant. Look at because it is a vector, I cannot write just sigma. So this is I is a identity matrix. Okay, and here the VAD is an abuse of notations. In fact, it is variance covariance matrix, and that's why we have sigma square I. I is a identity matrix. Okay, so for some of you, if you are not familiar with the basic knowledge of the matrix, I will request you to go through a basic notations of the matrix so that you can understand all those things later. And I hope you will get the slides and you can study at your home. Okay, so these are what do we mean by I have talking about here expectation and variance. So this is basically mean that when I'm talking about the expectation of a vector, basically I have to take the component wise expectation in each cases, and variance of y of a y vector is basically you have to multiply y minus expectation of y and y minus expectation of y of transpose that, and that will be ended up with all those things. But if you are not interested in theoretical stuff, you just may ignore all those things. You do not have to know everything. If you are just your objective is to apply linear regressions and get the results out of that, because the software will do the work for you. Okay. Similarly, just sake of completeness, if you have a covariance there, that basically means this quantity. I'll not go into that detail. Okay. So there are some basic random vectors things here. So here we have a non-random matrix and A. So this is the vector, and if you multiply just things, so you can think of A is a constant and A will come out here. And when I'm talking about variance of AY, we will have A here and A transpose here, and variance of Y is there. And similarly for the covariance part. So you may skip this one. Okay. So now we'll come to the most important part, that is the interpretation of the regression coefficient. Okay. So the estimated beta using the least square estimation process, we will have this beta hat to be x transpose x whole inverse x transpose y. Okay, so this is the general form. If you also apply if you have just two parameters like beta naught and beta 1, you can also find the whatever estimate we observed yesterday, you can still get those estimates, because simple linear regression is a special case of multiple linear regression. So whenever you have doubt on something, you just, with respect to multiple linear regression, you just put p equal to 1, then it will solve the purpose and it will go back to the simple linear regression. Okay. So here the estimated least square regression coefficient have. Is there any problem? Is someone unable to listen my voice, or is it okay?
It's fine, sir. No issues.
Okay. Someone wrote something. Okay. Thank you very much. So here. Most of time these you should have a good accent of English. What I mean that you should understand the basic concept and to explain very the person with you end. Okay, you know that beta here, beta 1, beta naught, beta 1 up to beta p. Okay, and this know these things that when I put everything is equal to 0, so that means you just remember the regression line. The expected value of the no effect of input variable, beta naught represent what should be the expected value or average value of the response variable or the target variable. Now the problem is that it may not have any physical interpretation, since 0 value for the predictor might not be impossible, might be impossible and might never come close to the occurring of the observed data. Suppose you are talking about like so if you are talking about something like height versus weight, okay, or the weight as a responsible variable and height, and you are also taking about the age. So input variable is height and age. And weight is the outcome variable. Okay, now, so now if you want to see the impact of age on, so you need to put 0 value to the height, but height in 0. Then, so that means if you have original variable like x1 as the height, so what do? You transform that variable like x1 star if you want to interpret, otherwise it's still fine. X1 beta 1. So I will put all the else here to be fixed. That means they are not changing. Now, if I change 1 unit change, that means I am changing x1 value to something x1 plus 1, so that the effective change is only 1. Now, if I change only 1, so that means that will be reflected the change in expected value of y, that will be beta 1. Okay, so is it clear? Is it clear to all of you? Hello?
Yes, sir.
Great.
Yes, sir.
So that means that if I'm telling once again, because this is very important, the interpretation of beta 1 is that when everything else is fixed in the model, I'm not changing anything else. If I change the value of x to something, say for example from 10 to 11, then this value changing is 1. So this effect is cancelled out. So and this beta is already fixed to 1. So this change is only, so when I change the unit value in x1, and the effect of change in expected value of y is the interpretation or is the value of beta 1. Okay. So here the word associated, so this is very important. We cannot say that the change in the target variable is caused by a change in the predictors. Only that they are associated with each other. The correlation does not imply the causations. Okay. So causation, what I'm a lot of time we fit a regression and we claim that this is causing something this, but in statistics, causation is a very, strong word. Causation means that if I do something, then something will happen. Okay. But here, this is not causation. Say, for example, if you are talking about the weight versus height, so that if you say that your, say, for example, this is weight, and if you have a in inches 30 inches plus 2.5 into height and plus some like 0.8 into age. Okay, so that means does not mean that if you increase someone height is increasing 1 unit, that does not necessarily increase the weight. You have already seen a lot of people whose height is very high but weight is not that much. So there are a lot of variabilities. So that means here the association that I'm talking about, it's not causation. It's not that if I increase height, the weight will definitely increase. In some cases, if you, in some specific example, if you increase height from someone who is obese, your weight can actually decrease. Okay. So that is the thing. So here I will say that height and weight are strongly associated, but I will not say that they are causally related to the thing. So causation is a much more stronger word that I will say. So here, if I want to interpret that on average, if the height of a person increase in 1 unit, so that will effectively increase the weight to 0.5. So if it is in kg, that means it will increase the 2.5 kilograms based on this model. But in case of some individual cases, it may not hold as I'm telling you. Okay. So another key point is that holding all else in the model fixed, implication of which is often ignored. So here I'm talking about the increase the weight. But in practical situation, you have to think about height does not increase over, just a 1 day. So when you increase height, if my height is increasing 1 inch, that means my age has to have increased. So physically interpreting is that does not make any sense when I'm talking about the increase your height, keeping other variables fixed in this particular model, because that is not possible because I cannot stop my age. So those things you need to be keep into the mind. So something I am telling for the interpretation, but in practice, those things with respect to the model that you have defined may not be valid at all. Okay, now the theory is over. We'll talk about one example so that you can connect the things from your end. Okay, so here is the data example, and it is about the childhood respiratory disease, and we are talking about the one specific variable of interest that is called the FEV, that is the forced expiratory volume, and is a index of the pulmonary function. What is measured? It measures the volume of air expelled after 1 second of constant effort. Okay. So FEV is the measure of the volume of air expelled after 1 second of constant effort. Okay, and this data set contains the FEV of 654 children ages 3 to 22 who had seen a specific study that is called the Childhood Respiratory Disease Study in 1980 is Boston, Massachusetts. Okay, anyway, so the data is a part of larger study to follow the change of the pulmonary functions over time in the children. Okay, so this is the main objective or the research question was the change in pulmonary functions over time in children, and you can download this data from this link. Hope that link is working for you. Okay, so I'll read the data from our end, and before I go, so do you have any questions from whatever we discussed earlier? Anyone? Can quickly discuss 1 or 2 questions and then go there. Okay, no question. Okay, so we'll read the file. So you can read the file. This is the CSV comma separated file using this command. So the variables that we have ID number, they have one ID number, and age in years, FEV, then forced expiratory volume in liters, and height in inches, and sex, male or female, and smoking status, non-smoker and current smoker. You might ask that their child, why should they smoke in a specific country? Because you remember the age is actually 3 to 22, if I remember correctly. Yes. So there will be some cases that they can smoke, or sometimes people smoke outside their home without informing others. Okay, so these are the variables that we have. Based on that, you want to build a model using the multiple linear regression. Okay, so these all the commands are already familiar to you, and right now we'll infer. So we have a data, and we first think that we have to know what the data are talking about, all about, without going into fitting the model first. So what we will do, first thing, I generally do the head D. It will print the first few lines of the data. Okay, so here it is the ID, age, FEV, height, sex, smoker. So these are the ID. I don't care about ID, but here is the age variable, and I can see the different numbers. The FEV values are there. Height is also there. Yes. Yes, someone is saying something. Okay, never mind. Male or female, the binary variable, and smoking status, I think non-smoker and smoker. Okay, so I also print the tail, sometimes printing all those things, so whether just to check different options so that your data is correct, or there is any missing values, observations, or some things which is apparent. So that good thing that if you have a data, you print the head, the tail of the data, sometimes from some portion of the middle. If it is the fit in Excel file, you can just scroll down, but if the data set is very, very large, then you need to check from printing from the different parts of the data, so that that is basically cross-checking everything is fine or not. Okay. So just because here you can see that current smoker and non-smoker, but here all the non-smokers, and from only printing this, you might think that there is no other things, but here you can see all those things. And you can print the column names. What are the different column names in the data? So in this case, you are familiar, but if you have more variables, then it is very good to print that how many columns are there and what are the columns names, if that is available to you. Okay, so STR, that is the short form of the structure of the data D. And this is very important. It is a lot of information. We have 654 observations and 6 variables, and ID is integer, age is integer, FEV is number, height is number, sex is factor with 2 labels, basically the female and male, and smoking is also, smoker is also factor variable, with two labels, current and non-current. Okay, so here things are pretty good for you, but in general things will not be that good for you. So maximum time when you are working as a statistician or data scientist, so thing is that your 80% work will be devoted to clean the data, and rest of the 20 points model fitting and interpretation. So that has been pretty much simple things, but you will not get the data in a pretty good format. So you have to have a very good programming knowledge to clean the data. If you do not clean the data, your results will be very much difficult to understand, and sometimes maybe totally wrong based on the unclean data. So for example, when you are talking about the variable, categorical variable, sex or smoker status, so you need to make them factor variable. If it is number, the interpretation may be different with respect to what kind of software you are using. So you need to be very, very careful. It's not just that if you have an Excel file and just straight away feed the things. So you need to understand the implication of whether any factor variable is there or character variable is there, and those things needs to be checked pretty carefully. Okay. And I will come into that with respect to factor again in the few more next slide. And I also print sometimes head of this 50, or you can just print the entire value if it is not too much, so that you can have a feel of what is going on here. Okay, so here also you can print the any specific row if you have any information about the any specific ID or something like that, and you can also print some portion of the data with this command. So we'll go through again all those things in the lab. So my objective is that whatever we are presenting, we'll also replicate those things into the lab session, so that if you do the same thing again and again, even in the short span of time, you will learn at least something that you can take away from this workshop, and later on when you come back again by yourself, so that you should be able to do things by yourself. That's the objective from our end. Okay, now the summary. This is very important command, and it will give you the basic idea. ID I don't care, but age is that minimum age is 3 and the maximum is 19, even though they are talking about that 22, but at least with respect to small data, we do not have anyone more than 19 years age. And FEV value, minimum value and maximum value there, all the other information is there. Height is also there. I know the minimum, maximum here. There are female members, the female child 318 and the male is 336. So this will give you roughly idea that if you have one of the group is very less, then you should be skeptical about your results. Okay. Here they are fairly well representative, but suppose you have just 36 male and rest are other females, then when you fit the linear regression, your interpretation about with respect to sex is you have to be very careful, because there are not many male into the population. So these small things are very important. It's not that you have the data and you just straight away feed. So depending on what kind of data, whether that actually represent. So right now you are fair enough that it is representing the society, because we understand the male-female ratio is pretty much generally in Western countries 50-50. In some cases it can be skewed, but generally like that. So if in your data it is not reflecting like 50-50%, then there might be some problem that data is not representative of the population. So whatever inference you will do based on that data will not be valid for the population. So objective of any kind of model, we have a small data that is the sample data, and we feed them any kind of statistical model, then go back and infer about the population. But you need to have a correct data for that. If your data is not representing the population, there is no purpose of model fitting. That data is not good for you. So here also we have a smoking status. Here also we have pretty much only few observation for the current one, and that is expected, because we do not expect children to be extremely high number of children smoking. So that is with respect to your prior knowledge or the basic science knowledge, your data is saying the exactly same thing. So that means data is correct. Similarly, you can go for the graphs for the several graphs, histogram. So I will start with the histogram of the FEV variable. Then you can change the number of breaks, and you can change the unit of the y-axis from frequency to density, and you can plot the density also. So these are like checking all those things. So here, this is the histogram, and this is the histogram of FEV. Just look that if we just change the beans, the perception of this distribution is pretty much changing. Okay, so that means that why yesterday I talked about why you should not check for the normality with respect to histogram, because of the structure, because depending on the bean size, your shape of the or the perception of the graph can change dramatically. Now here this is frequency, here we are talking about the density, and if you plot an approximate density, would be something like this one, which is you can say that approximately normal, but it's not exactly normal. Okay, so again, we can plot the different scatter plots like FEV and height, FEV and age, and FEV and sex, and FEV and smoker. Okay, so right now we are saying that this is the X variable and this is the Y variable, FEV. This is again another variable, age. This is the Y, this is the Y again, and this is the sex, and this is the smoker. Okay. So here I am expecting increasing relationship between the height and FEV. That means if height increase, I will expect that FEV is also increasing. And if the age is increasing, I will also say that the FEV is increasing. Okay. Now, with respect to the categorical variable of these two variables, we cannot have this kind of plots here. We have to go for the box plot. So here, with respect to the female and the male, I can see that FEV value is slightly higher in case of the male children compared to the female children. Okay, and also the number of the distribution is far more of the extreme values is corresponding to the male participants. Okay, similarly for the FEV, the current and the non-smoker. Okay, somehow this is kind of counterintuitive. Okay, counterintuitive in the sense you are saying that who are actually smoker, their FEV value is higher than this one. Okay, so that means intuitively you say that if you smoke, some children smoke, their FEV value is expected to be higher. Can anyone explain why we are seeing this one? So this is not what our perception is. So here from this picture, what we are saying that, or what we are observing that, who are the smoker, current smoker, their FEV values is currently higher than the who are non-smoker. Anyone? So this is the actually good example why you just not blindly do anything so that your interpretation is lost. Here there is a hidden information. Who are the current smoker? Current smoker will not be of children of age 3 to 10. Those current smoker has to be some higher age. It will be, or in a practical sense, they will be more close to their 20s. So they are corresponding to who are non-smoker. Their average age is actually has to be higher. That is our basic sense or basic knowledge is telling. That means they expected to higher FEV irrespective of this smoking status because they are far ahead, and far older than the average non-smoker. And that is the reason we are seeing this kind of things. Okay, so if you do not observe these kind of things, your interpretation will go into the wrong direction. So as a data scientist or statistician, you need to be much vigilant about your data. It's just not about, I'm saying again and again, it's just not about that you have a data and you just straight away feed. There are a lot of hidden information is there that will make sense. And when you actually write some paper, if you can incite some of these things, that will people actually read. I mean, otherwise, just with the data or in a statistical software, anybody can feed. I mean, you do not have to learn all those things. You just tell a class 10-year students, and they can do that one. But what make you as a statistician or data scientist is that how do you interpret and how do you connect things with your data. And for that data, you need to understand that your data very, very carefully, and that require a lot of skills to understand all those things. Now we'll fit the multiple linear regression here with intercept. That means I have the beta naught here, and this is the command that you already know. Here we have more than one variable: height, age, sex, and smoker. Okay, so here is the fitted regression line, and residuals are something like that. Minimum is minus 1.37 and maximum is 1.9. Okay, and the coefficients are like intercept, height, age, sex, non-smoker. Now, with respect to these two categorical variables, there is an important distinctions is that sex, male, smoker, non. Okay, so if you remember that the category for the sex is male and female. Okay, so here sex male means that here the baseline is taken as a female, and these estimate correspond to the male. That means that when I interpret results, I will consider that if I increase from female, or I should not say increase, if I change one observation from the female to male, not the opposite one, because this of male, I have written male, that means my baseline is female, and from that baseline, if I switch to male, that is the thing. Similarly, for the smoker, this is non is written, that means the baseline is the smoker. So if I change from smoking to smokers to non-smoker, I cannot do the opposite because of this. I mean, the model is fitted with respect to considering smoker as the baseline from smoker to non-smoker. Okay. So this is very important distinction. And if you do not see that this extra term added when you fit the regression model, then you have not converted your observations or the categorical observation to the factor variable. That's a good check, and you have to go back and check all those things. Okay, so these are the estimates. I will come into again later on, and these are the standard error, that means the square root of the variance, and these are the t values, and corresponding p value are all are there. And multiple r square value is 0.77, which is pretty good, and adjusted r square is also close to that 0.774. And p-value, the F statistic, that is also significant. Excuse me. I'll come again with the explanation. So let's go with intercept. So this is another important topic that a lot of people do not know and just blindly do that and get something wrong results. So without intercept, what you have to do, you have to just to take -1 here, and it will do the job for you. So look, there is no intercept down here, only the variable starting from here. One of the problem here that you notice the R square value here, 0.97. Earlier it was 0.77. So what you did, you just put 1 minus 1. So without intercept, your R square is pumping up, and it is extremely good R square. But let me warn you, for the no intercept model, R square is not a valid measure. In fact, if you just remove the intercept from any regression model, any multiple regression model, the R square value generally will show on the higher side. Okay. So this is very important observation. So if you just remove the intercept, and your R square will pump up, and whenever you have a no intercept model, that is not a valid measure. And now the question is that when do you go for the without intercept model, or when do you go for with intercept model? So general idea is that if you have some model, and your basic knowledge is saying that if I put all the independent variable value 0, whether my outcome will be 0 or not. If by definition of the basic science area that with the data you are working on, if you find that, or if you put all the variables to be 0 and physically that value has to be 0, then you can think of without no intercept model. But you need to be very much careful when you are trying to explain the without intercept model, because of this a lot of things are there that you need to take care of. Okay. Now we'll go again the interpretation of these models. So we have this is the original model with respect to beta 1, beta naught, beta 1, beta 2, beta 3, beta 4. Now, finally, with the fitted model, we have this minus 4.54, that is basically coming from this here, then 0.1 and 0.06, 0.1 and 0.07 are rounded off, 0.16 and 0.09. Okay, well, we have these results here, so we do not have to go back. Now, what does it mean? This means, for example, so if I'm talking about the FEV value with respect to height, if I consider everything is constant here or I'm not changing anything, I will say that if the children height increasing 1 unit, that means 1 inch, I expect 0.1 change in the FEV value on average. So first thing you notice the change, I mean the plus sign here. That means plus sign saying me that if height increase, FEV is tend to increase. Now, what amount? If I keep everything else into the model fixed, if I change the height value only 1 unit, I expect the on average is very important. In specific situation is might different, but on average, I expect 0.1 unit of change in FEV because of 1 unit change in the height value. Similarly, age is there. So when everything else is fixed, if someone's age is increasing 1 unit, that means it could be 1 year, something like that, then there will be also increased 0.07 unit of FEV value on average. Okay, now what about the categorical variable like sex or smoker? So remember that when I'm talking about the variable sex, I'm talking about with respect to baseline female and male. That means that compared to a female participant, male participant or male children will have 0.16 more unit of the FEV value. That means on average, from a female child to a male child, it is expected to have 0.016 more FEV values. So that is the correct interpretation. Similarly, for the smoker, if someone is more, so this is the non, so that means my baseline is the current smoker. From a non-smoker child, if someone is non-smoker, he or she should have at least, around 0.09 more unit of the FEV value. Now this makes sense. So look at this. So even in the box plot, you show something counterintuitive, but here things are explaining well. But notice that the p-value corresponding to this is not significant, probably because we do not have much more data. So if we go back to the data, where is the data? Yeah, so we have compared to the entire data, we have only small amount of currently smoking, which is good, but from the data perspective, it is a small data, and that's why we might be seeing. So there might be other reason also, but this is not significant. All the other values are significant because the p-value, if you set your alpha equal to 0.05, everything is less than 0.05. Okay, and so on. So these are all significant value, and so this is not one. Yeah, all these 0.05, so all are significant value. Okay, so in nutshell, what I will say that in this particular model, we find that the variable height, age, and sex is significant, and they will have some effect. But smoking variable, it's not significant, but still it has some effect with respect to if someone is non-smoker, he is expected to have a higher FEV value. Okay. Now diagnostic plots. You have already seen all those things earlier. Here I expect things are like to be followed randomly, but still you can say some kind of pattern, and that is actually saying that there is some kind of non-constant non-constant problem might be there. Okay, and that is also expected from this graph. This is not totally at random in a straight line in two way, but there is no problem of the Cook distance because I could not find any problems below the red dotted lines here. And from the QQ, that is normality assumptions, it is not, there are some problems here, but practical purpose, I can ignore this one, but it is up to you whether you want to ignore practical purpose. It's still fine, but it's, if someone is interested, it may be advisable to go for some kind of, I mean, or at least check that whether you can correct that with respect to some transformation or not. Okay, now we have done everything. We will go for the predictions, and here the few commands that you already know about that, and you can find out the coefficient. All these coefficient will be there. Okay, for the prediction, so you can predict, those are already, so these are the already fitted values based on the, so that is, suppose you have in observation, and these are all the fitted values, and with respect to lower boundary and upper boundary of the predictions. But for the new data, suppose you want to know that you have a new candidate whose height is 61 inch, age is 8 years, sex is female, and smoking status is non-smoker. So what, based on your model, what will be the FEV value? What you have to do, because you have stored everything in the reg, reg object, so you need to call with respect to predict.lm that object where you stored your regression model, and you need to put the new x at the new data, and interval is the confidence, so it will give you the, so this is the predicted value corresponding to this candidate child with respect to lower confidence limit and upper confidence limit, that is the fit value is 2.42. Okay, so this is done. Any questions after this? I'm surprised. Last day you asked so many questions, and today there is no questions. Either you are understanding everything or you are understanding nothing. Okay, so we are almost halfway. Now we'll start the logistic regression. Am I audible?
Yes, sir.
Okay, fine. So we'll start logistic regression. So whatever we have learned, we have learned the simple linear regression and the multiple linear regression, and we have also learned how to implement all those things into the R statistical software. In the lab sessions, you will also learn, I mean, whatever the data I have shown here, I will have, I mean, in front of you, I will just explain all those things into the R and R Studio so that you can learn things from your end also. Okay, so we'll talk about the logistic regression right now. So model for the binary data. So before we are starting, what is the binary data? So we will talk about some of the examples here. So binary response variables are quite common in practice, and here are some examples. So you can think of the detecting the efficiency of a medical toolkit. I'm giving malaria, but you can think about the COVID. COVID is here, so it is easy to connect. So whether a testing kit like for the COVID testing outcome is COVID positive or COVID negative, like yes or no, that is the binary outcome, or use of contraceptions. So that means that is also binary, whether using it or non-using it as the response of the dependent variable, or this is the use of, that means binary variable, and the other variables like age, education, and desire for more children, they are the predictors. And you can find this study here. And habit and preference of the lizard, so shade versus sun. So all these examples like binary outcomes. So, and I have given so many examples so that you can connect things that are how important this kind of models, and various kind of people with different backgrounds may are actually using those kind of regression model or the logistic regression model. Okay, so here the credit models to evaluate the risk of a consumer loans in banking sector, defaulter or not. How many of you will have more than 1 crore before your 40th birthday? It's not possible for me, but surely for some of you, you can. Some of you will be achieve 1 crore before 40th birthday. Okay, so will you have safe drinking water access when you are over 40? That is again the binary outcome we are talking about. And look at the diversity of the different examples that I have chalked out for you. And will you develop cancer before 40 if you smoke, take alcohol, or use drugs? Okay, so will you find, this is very important, will you find this class helpful after 10 years from now? That is again binary, yes or no. Okay, let each individual or experimental unit that we are talking about, the response variable or the outcome variable y can take only one of the two possible values, yes or no. For convenience, we denote them as 0 and 1, but you can denote with anything else like 101 and 350, something like that. There is no harm of that, but the interpretation will be problematic. So you can take any two values, whatever your choice, but the interpretation will be problem and it will be very difficult and messy to interpret all those things. Okay, generally 0 refers to the failures and 1 refers to the success. That is again like failure means no and success is yes kind of thing you can think of. Okay, so here we have two outcomes. Probability of failure and success F. So probability of y equal to 0, that means probability of failure, that is denoted by 1 minus pi I. I denote the corresponding participants there, and yi equal to 1 equal to pi I, that is the corresponding to the ith individual or ith participants. What is the probability of y equal to 1, that is equal to pi I. So in design experiment, by design experiment, I mean where you actually conduct and everything is under control. You design and then the participants are recruited. Or surveys where you just take the examples, or observational study, just observe from a database or something like that. For each individual or experimental unit, we have a vector of covariates or explanatory variable that we already seen in case of multiple linear regression. For each experimental unit or participants, we have a vector of covariates or explanatory variable x1, x2, xp. Okay, so here the principal objective of any statistical analysis is to investigate the relationship between the response variable, that is y. Here we are talking about the probability pi and the explanatory variable. You remember in case of regression line, we just talking about this kind of things with the relationship with the outcome variable. But generally, we put in case of linear model, that is basically multiple linear regression that you are familiar with, expected value of the outcome is defined by the explanatory variable. But here, if you calculate for the Bernoulli random variable, expected value of yi is equal to pi I. Now, if you are trying to fit a linear model here, then you have to equate pi I with respect to this one. Can anybody point out what will be the problem if I just directly fit the linear regression here in this format? Anyone, any thought? Someone said that voice is not coming. Is it true for others? Can you hear me properly? Hello?
Yes, sir, you're audible.
Okay, fine. So let's, by forcefully, I will try a linear model here. Now, what will be the problem? Why not linear regression that you have already learned, like simple linear regression model or the multiple linear regression model? Why this is not working for the binary data? Okay, so here the least square modeling is not a possibility or not reasonable for following reasons. What are the reasons? That yi is not normally distributed, it can take only two values, even though normality is not required for the estimation purpose. Okay, so fitting classical linear regression model, you can make the probability of success to be outside range. So if you fit like something like this one, so if you predict something, these values will not, I mean, it can take any values from minus infinity to plus infinity. It will not be inside 0, 1, but you know that pi pi I has to belongs to 0 and 1. Okay, this pi I I'm talking about, this has to belong to 0 and 1. Okay, so that is the problem with the linear regression. And a linear model implies that a specific change in the predictor variable is associated with the same change in the probability of success for any value of the predictor, which is unlikely to be the case. So this is the exact example that we are talking about. So specific change in the predictor variable, that means X variables, is associated with the same change of probability of success for any value of the predictor. So when I'm talking about the change in X, like I say that change in 0 to 10 to 11 or 100, 1 to 100, 2. So 1 unit change here and 1 unit change is here does not make any difference in case of a simple linear regression or multiple linear regression. But here that is a problem. And we have at least one example here. For example, consider a firm with extremely high debt, okay, is likely to have very high probability of bankruptcy. So you consider some firm, whatever firm you can think of, having very high debt, and that means that they have a very high probability of bankruptcy. Okay, now for such a firm, we can reasonably think that increase of debt of 1 million, say, I'm increasing the debt to 1 million, that would not be associated with small absolute change in the probability of bankruptcy. So think about again. So you can think what I'm specifically talking about. If you are having difficulty to understanding these examples, you can think of the marks. Suppose you obtained 98 marks in a math exam. Okay. Now you can think of, if you want to increase your marks from 98 to 91, how much effort you have to put. Now, on the contrary, you think about that you obtain only 40 marks in the math exam, and you are in the next exam, you are trying to increase the marks 141 to 40 to 41. So what am I pointing out that if your debt is very high, that means around the 98 marks corresponding to marks in math, 98 to 99, that 1 unit increase here, and 41 to 40 to 41, that is, those are not same amount of effort is not required for increase of 1 marks here and 1 marks here. So basically bankruptcy, so which is already very high probability of bankruptcy, it does not matter if you increase the debt 1 million, because it's already high, it will not affect. But on the contrary, such as increase in debt would be expected to have much larger effect in probability of bankruptcy for a firm with moderate debt. So it's like 41 to 40, 40 to 41. If you increase for a moderate debt fund 1 million, that's a huge money for them. Even it is 1 million for the same two. That means that change will have much effect on the corresponding bankruptcy probability, because it is not the same like as in linear regression 10 to 11 and 101 to 100 change. That means from where I am changing, it does matter in case of when I'm talking about the success probability pi I, but not in linear regression. So that's a very distinctive feature that I would say, and that needs to be taken care of when you are talking about the logistic model. Okay, so these are the lot of intuitive ideas that came into the picture when you are talking about the logistic regression. So similarly, you can think about the opposite relationship if you talk about the in terms of the not debt, but the revenues, but with the relation of bankruptcy, you can think about by yourself. Okay, so the behavior of the model should be consistent with the known physical or biological or mathematical laws, especially in its limiting behavior. So the models came from some intuition. In statistics, your intuition is the key. You need to see something. Okay, and I say only two people in this world can see the futures. One is God and another is statistician. Those who can see the future. Okay, so as a statistician, you should have some kind of like intuition to things, what should be that, what should you expect, and then you should formulate what kind of model you can build up there. Okay, and similarly, in terms of that change 41 to 40, 40 to 41, or 98 to 91, those changes are not same, you already understand that, and based on that you need to the model. Okay, so the linear model that we are talking about, an important role in practice, and here where what we are doing about, here we are talking about the dependence of the success probability pi on the x1, x2, xp occurs through the linear combination, and this is given by this. So this is exactly same thing whatever you observe, x multiplied by beta in case of linear regression, the right hand side of that, and you are naming as this eta for some unknown coefficient beta 1 to beta p. So unless there is any restriction imposed on coefficient beta, those eta can take any value minus infinity to plus infinity, and because of that I cannot just equate them with respect to pi I. Okay, so this is the things. Now what can I do? I need to do something. So I cannot change this. So I have this and I have this. I somehow I need to relate these two things with respect to something, so that the mathematical explanation should be valid. Okay, a simple and effective way to avoid this kind of difficulty is use a transformation g pi that maps the unit interval onto the whole real line. So earlier I have something eta which is minus infinity to infinity, and this pi is 0, 1. So the simple intuitive, I need to define some g pi which is belongs to 0 to 1 to minus infinity plus infinity, so that I can equate them without any problem. So in generalized linear model, that is a far more advanced concept than the linear regression. Generalized linear model, which is a special case of that, is also the logistic regression and also the simple linear regression and multiple linear regression. So we are talking about a link function there, and that is basically g pi. So I will equate g pi with that because I have already taken care of that minus infinity to plus infinity things. Okay, so there are wide choice of the g pi available, and one of these choice is the logit or logistic link. There are other like probit model, log model for the different choice of the link function, but I will not go there. So we'll just concentrate on the logit or logistic link function, and that is defined by this one. Now this is log function, and this quantity is something always positive because pi lies between 0 to 1. What is log function look like? So if you put this is x, and if you put the log function, it will look like something like that. Okay, so and this is plus infinity and this is minus infinity. So now with respect to this positive quantity, when you apply log before that, that quantity becomes in minus infinity to plus infinity. Okay, so now I can equate this g1 pi here, so that this equality makes sense because this value can take any value in minus infinity to plus infinity. So my problem is solved right now. Okay, so what we'll do, we'll use the link function g1 pi for the logistic regression with two covariates x1 and x2. You can add more covariates, and so basically my models become log of pi by 1 by pi, beta naught, beta 1, x1 p. So this can take any value minus infinity to plus infinity, and with respect to log, this also can take any value in minus infinity to plus infinity. Where log of pi, this is actually the log of odds of a positive response. So this quantity is actually called the odds. And if you take log of that, it is called actually log of odds. So here it is basically log of, because you are putting here pi is the probability of success. Sometimes it's called the odds of success. Okay, so odds means that probability of something divided by opposite probability of something. Here in this case, probability of success divided by the probability of failure, 1 by pi. Okay, if you just take these logs, so just take e to the power something both side, then it will become the 1 by pi here, and you will ended up with this one. Similarly, after some calculations, just first reciprocal pi by 1 by pi both side, and then just take plus 1, then this pi will cancel out, and then again doing the reciprocal, you are ended with these things. You can check. This is very easy algebra. You can do it anytime when you are free. Okay, here the pi is the probability of the positive response. We know that already. The last line represents the inverse of the G pi. Okay. And here now we'll talk about the interpretation. That is very important part. Here, what we have here, the interpretation is the effect of unit change in x2 is to increase the log of odds by amount of beta 2. Okay, so when I'm talking about the increase in x2, so if I increase the value of the x2 from 1, so say for example 10 to 11, now I don't care about the what value because all the transformation is already made. So if I increase the 10 to 11 here, and when everything else is fixed here, so this is the interpretation of beta 2. So is the unit change in x2 to increase the value of the log odds by amount of beta 2. So unit change in x2 will increase the value of the log of pi by 1 minus pi. That is basically the log of odds with the beta 2 amount. I'm telling again. So interpretation of beta 2 is that it is the change in the log of odds for a unit change in x2 when everything else into the model is fixed. Okay, so equivalently or more important, preferably, a unit change in x2 is to increase the odds of the positive response variable multiplicatively by factor e to the power beta 2. You are coming from here. So now I am not talking about the log of odds, I'm talking about the only odds, and that specifically corresponds to the this model. So when I'm changing, so when everything else is fixed, so if I change here 1 unit, so the log of odds, so there will be 2 cases, one for 10 and another for 11. So 2 regression, I mean 2 lines will be there, and if you divide by them, one by of them, then you will see that in the second case, the ratio of these 2 will be changed by e to the power beta. This is a very easy to change. I mean, easy to check. You just put 2 equations and divide each of them. You will see that how the things is going on. Okay, so in both cases, in the or both scenarios, the x1 has to be fixed and not to be permitted to vary as a consequence of the change of the x2. We already said about that. And note that, as I told, the direction and the magnitude of the stated effect are unaffected by the variable x1 and x2. So that means I'm talking about the change from 10 to 11 or 101 to 102, doesn't matter right now. Earlier it was a problem, but after the logit function or introduction of the logit link, we have solved that problem. So that is not an issue, thankfully. Okay, again, we'll talk about one example here, and it is a very interesting example. Any questions after this? Okay, no questions. So we'll talk about the logistic regression in R, an example. And this is going back to the January 1986. So Space Shuttle Challenger exploded shortly after launch. An investigation was launched into the cause of the crash, and the attention focused on the rubber O-ring seals, the rocket boosters. So we are talking about one incident of the Space Shuttle in 1986, and it's called the Space Shuttle Challenger. You can search in the internet and you will find that what was all about it. And it was exploded shortly after launch. And after the launch, after that incident, an investigation was there to find out the cause of the crash. And the main focus was on the rubber ring. Okay, so rubber ring, basically rubber ring cells. And the idea or the knowledge that we have at the lower temperatures, rubber becomes more brittle. Like brittle means that it has become more hard, that it can actually break in lower temperature, and is less effective sealant. At the time of the launch, the temperature was 31 degrees Fahrenheit, so much cooler. Okay. So the concept was, or the question was, could the failure of the O-rings have been predicted? You need to understand this is a high money game. So as a statistician or data scientist, whether we could have predicted that what happened, like the explosion because of this low temperature, because the temperature at the time of launch was known to you. So if you can build a model and that can predict that there is a high chance of the explosion, so you can postpone the prediction because a huge money could have been saved. So this is the basic examples that as a data scientist or statistician, you will have much power to change or impact the human life and the at large. So the statistics is a tool that will give you a lot of power, but you need to use that power very responsibly, because if you are do something wrong, that have much dangerous repercussion or the attack that you can have in terms of money, or you can have in terms of the human life. Okay, so whatever the data we have here, 23 previous shuttle missions with for which the data exists, and some evidence of the damage due to the blow by erosion was recorded on some O-rings. Okay, so someone is only interested in attendance, not for the talk. Interesting. Okay, so here each shuttle had 2 boosters, each with the 3 rings, 3 O-rings. That means that we have total 6 O-rings out of, and the question was that the number of O-rings out of the 6 showing some damage and the launch temperature. So data we have the launch temperature for each of these cases, and how many of the 6 O-rings have some amount of damage. Okay, and this is a very simplification of the problem C, the main problem for entire problem C, this paper or this chapter from the book by Julian Faraway, Extending the Linear Models. Okay, so the library here is that you can have this library and to get the data. So data is O-rings data, and we'll also in the lab session we'll talk about this data again, and with this all these commands step by step, so that you can have a feel and what we are doing. So it's a, if I str O-rings, then it will have 23 observations, 2 variables, and both are the numbers. These are the temperatures, and these are the like number of damages. Okay, so I will say the books at the end of this PDF. You will have the reference, so you don't need to worry about that. Summary of O-rings. So this is the summary. The temperature, maximum temperature, minimum was 53 and maximum is 81. Damage is, minimum is 0, maximum is 5. And if you take the head of O-rings, this looks like this. Now we will plot this damage versus temperature from the O-ring data. This is the scatter plot. Okay, table here, you will see that there are 0 damage in 16 cases. Okay, and 1 damage in 6 cases, and 5 damages in 1 cases. Okay, so this is denoting that 5 damages, this one, and this is denoting 6 damages here with respect to 1, and rest of other the 16 damages. Anyone see any problem here? Any problem you noticed?
Is it that it's not a linear function?
Yeah, it is not a linear function. That's a good observation. But also see that here I am talking about the 6 observations, and here you have only 5 of them.
Okay, sir.
But that is also a good observation. But why? Because there are, I think, for these 70 observations, can think about a linear regression there. So we are interested in how the probability of failure in a given O-ring is related to the launch temperature, that is my X variable here, and predicting that the probability when the temperature is 31. So I know that the corresponding incident when happened is 31 degree Fahrenheit, and we are trying to predict the what was the probability of explosion based on the data that we have. So you can of them. Okay. So what we'll do here, we'll do a logistic regression there that we have just learned. And here our objective is to fitting a logistic regression to the above data with damage and non-damage as the binary outcome variable. So here we are talking about a binomial random variable. Out of 6, how many damages are there? So 0 is 1, and any other damage is categorized as a combined as a damage. Okay. For the binomial response data, we need 2 pieces of information about the response values y and n. In R, this is very useful. One way of doing this is to form a 2-column matrix with the first column representing the number of success y, and the second column is the failure n-1. So you are talking about C bind means that you are combining 2 columns. C bind means column bind. So damage and max 6 minus damage. That means it is y and this is n-y. Okay, just these 2 things here. Read again. One way of doing this is to form a 2-column matrix with the first column representing the number of success y and the second column number is failures n-y. So we have specified that response is binomially distributed and the default choice of the link is logit for the logistic regression, and the default choice is also the logistic regression in case of R. Okay, so fit the data here. Instead of earlier we are talking about the LM, and because it is put a lot of variables into the model, and that is acting as a penalty in that case. And this criteria has an advantage generally and can be applied to beyond non-normal linear models. Okay, so AIC is very general. You can also use in the regression setup also to find out that whether two models are which one is perfectly working for you. So AIC estimate the quality of each model relative to each other. So this relative is very important to each other. Thus, the AIC provides the means for model selection. So if you have several models or several predictive models, which one you will choose? You will choose that model, which one with the minimum AIC value or Akaike information criterion value. So AIC rewards goodness of fit, but it also includes penalty that an increasing functions of the number of estimated parameters. So if you add more parameters into the model, that means more variables into the model, it will add one penalty, because sometimes adding more variable can superficially give you a better result, but when you go for the testing, it may not be the good idea. So penalty discourage overfitting, because increasing the number of parameters in the model almost always improves the goodness of fit. Okay, so we quickly interpret. We are almost close to the time bound. So we'll quickly interpret. We have fitted a logistic regression model with a number of damages as the response variable and temperature as the input variable using a software. We have these values of estimated beta. So I should have put this cap here because these are the exact value. Okay, and the corresponding p-values are always here significant, less than 0.001. The residual deviance is this, and AIC criteria is this one. So to interpret that, the effect of unique change in temperature is to decrease the log of odds ratio, because decrease means because of this minus sign, by an amount of 0.2, or in other words, unit change in temperature is to increase the odds of positive response with respect to e to the power beta that we are talking about. Actually, e to the power minus beta, that is comes out to be 0.8. Now, the prediction that we are talking about, our main objective, whether to know that what will happen when the temperature is 31 degree Fahrenheit. So the logit fit tends to asymptotically towards 0 at one end and high to and lower temperature respectively. And the fitted values never actually reach 0 or 1. So the model never predicts anything completely certain or completely impossible. And using the iLogit function, which stands for the inverse logit, and it provides the estimated value of this success probability pi for the input of this kind of things. And we have estimated beta naught here, beta 1 here, and this is the 31 degree Fahrenheit temperature. And it turns out that probability of pi is equal to 0.9, and that is very high. So with a very high probability based on this temperature, we are saying that there is a almost like very high probability that it will be a failure. So had it been someone fitted a logistic model there, he or she could have predicted that there's a high chance of this failure because of the low temperature, and millions of dollars would have been saved if you postpone that that launch on some later day with a higher temperature. So that was the major objective of the logistic regression, and you can feel sense of that what is going on. Okay, so I'll just say, so a lot of things I have not covered here, like the variable selections, the multicollinearity. So all things are due to the time constraint we have not spoke about, but in machine learning literature, there is a concept of training data and test data. So here we do a splitting of the data into training and test when the objective is predictions rather than the measuring of association. So if you have data, you split the data. Sometimes it's 80% to 80-20%, and sometimes 90 to 10%. There is no specific rule, and you feed the model on the training data and do the prediction for the test data to check the accuracy of the model and check how things are going on. And if you have several models, you feed several models to the data and check the accuracy with the AIC, whichever is the smallest AIC, you can go for that one. And as I told, there are other topics like variable selections, and also there are syncage methods of like lasso regressions, ridge regressions. There are all kinds of regression there. I expect from here you will take responsibility by yourself to read all those books that I mentioned here, and also other books that you find interesting. So this is one book. This is another book I already mentioned. This is the book for the linear regression. This may be useful for logistic regression and other kind of models that you can think of. With that, I say thank you to you. That is everything from my end. If you have any questions, please go ahead. Any questions, or everything is fine from your end? No questions, so that means yes is not useful to you. Okay, I'll end this one. Let me stop sharing there. Yeah.
Okay, Palash. Thank
Okay,
you.
I don't understand whether they were asking too many questions yesterday, and this session no questions. Are they tired or they are not understanding? I don't know.
So one like question, sir, in case.
Yes.
Yes. Sir, in case if the magnitude of the data is different, do we need to scale in logistic regression? Like
magnitude in what sense?
means in case the independent variables, if the say it's a continuous data, no sir, like independent variables have to be continuous data. And in case if, for example, you are talking about height and weight, but the magnitudes are different.
Magnitudes means what is talking about magnitude? Magnitude is a unit.
Yes, sir. For example, if yeah, unit. For
Okay.
example, in case if I've got one as a centimeter and one I have got in kilometers, so do we need to scale in that sense?
You are talking about that one variable and different observation in different unit.
Yes, sir. Yes.
So if you are talking about height, one is in centimeter and another is like inches. Is that
Yes,
right? What
yes.
you're talking? Yeah, definitely.
Yes.
Otherwise, you are comparing with apple with oranges.
Okay. So in case of logistic regression, also that holds good, sir.
Yeah, I mean, not only for any comparison. So you are comparing, suppose in your model, when you feed the data into your model, so if you put 30 inches and 30 centimeter, it will not see the unit, it will treat both the observation on the same page.
Okay, sir.
Okay, so that will be definitely wrong. So your object, you have to change all before fitting the data, you change all those units into a single unit so that comparison makes sense.
Okay, thank you.
Okay, thank you. So if no more questions, I'll stop here and thank you very much. See you in the lab section. Enjoy the session with the Dr. Ryan Ganguly from here. Thank you.